Hi, I'm Charan. So now we are going to present a video on Lab8 assignment where we are going to analyze the frequency response of integrating circuits, differentiator circuits, and check the low pass effects and high pass effects of both of them. And we are also going to design an averaging circuit, which will basically average two sine wave signals, and give the output.
Okay, now we can see the circuit configuration here. This is the integrator circuit. We are using a 1 kilo ohm resistor and gave 100 nanofarad capacitor as feedback to the inverting pin. Now to this circuit we gave a sine wave with 1 volt peak to peak and 500 hertz frequency as the input. Now we are expecting the integrated wave, so we can see that in the output. We can see the phase change also. Basically, you can see the phase change. Now basically this circuit acts as a low pass filter that we can check by changing the frequency to 400 hertz. Now we should see the peak to peak value increasing because it's a low pass filter, so it will allow less frequencies with more it will give more output to less frequency signals. You can see the peak to peak is 3.6 volts. The previous one it is 1.2 volts only. So why is it acting like a low pass filter? That I am going to explain right now.
So now we'll see why the integrated circuit will act as a low pass filter and why the differentiator circuit will act as a high pass filter.
So basically this is the op amp minus inverting and non-inverting pin. Now in the integrator circuit, this is the integrator circuit, we are giving the input. Now what happens is, what is our input output relation for the integrator circuit? We have it has 1 by j r and c, j omega r c. Now what happens is, integrator circuit will act as a low pass filter. It acts as a low pass filter. Why? Because now if we have very high frequency signals, this the gain function will, if we have high frequency, if the omega is very high, then this approximately becomes 0. So which means the transfer function is 0. So the output is 0 approximately. It will become very less if the frequency increases. And if the frequency is very less, that means if the signal is of low frequency, so what happens, the transfer function will increase, which means the output of this circuit will be high. We can also think this in terms of the impedance of the capacitor. Now what happens is, for this impedance is 1 by j omega c. Now if we have very high frequency signals, what happens is we'll have some impedance here. So basically we are having some feedback. So the gain of the gain will decrease. So now if we have very low frequency signals, the impedance of this will be infinite, and basically this will become an open circuit. So we are not having any feedback from the output. If we are not having any feedback from the output, the output of the op amp will be the normal open loop gain, which is A. The gain will be open loop gain, which is very high. But if we do not have very low frequency signals and we have some high frequency signals, then we'll have a feedback from the output. So the gain of the op amp will decrease and will be some finite value which is less than the the open loop gain. So this acts as a low pass filter.
Let's see why the differentiator circuit acts as a high pass filter.
So in the case of a differentiator circuit, we'll draw the circuit diagram. This is op amp, inverting non-inverting pin. Now here we'll have the capacitor, and the resistor is given as feedback to the capacitor, and this will be given to the ground. Now in this case, what will be the transfer function? This is equal to j omega rc. Now what happens here is, here this will act as a high pass filter. Why? Because if you are having high frequencies, the transfer function is high, so we'll get high output. If you have low frequencies, like suppose very low frequencies, then will not get a good output, which means that this circuit is allowing high frequency signals more efficiently. This also we can think in terms of the impedance of the capacitor. Impedance of the capacitor, once again, it is given by 1 by j omega c. J is for phase, that's, you can ignore that. For 1 by omega c. Now if we have low omega, if you have very less omega, the impedance is very high. So which means that V in is not going to go to V out. Basically, if it is very high, this will become an open circuit and there will be no transfer at all. But if we have a high frequency signal here, then the impedance will be if we have very high, then this will almost be 0. So it will be a straight line. So we'll have V in and we'll get some V out. So we'll have good we'll get some output here. So that means it is allowing high frequency signals efficiently through the op amp. So it's a high pass filter.
Okay, so now let's see the frequency response of the differentiator and the integrator circuits. Now for the 1 ohm resistor, this is the integrating circuit.
Now we can clearly see from the graph for the lesser frequencies, lesser values of the frequencies, we have higher decibel gain, which means that the integrating circuit acts as a low pass filter. The same thing we can also see in the 2.7 kilo ohm resistor also. For the lesser frequencies, we have higher value of the decibel gain. So from here we can confirm that the integrating circuit is a low pass filter. It acts as a low pass filter. Now let's check for the differentiator circuit. For the differentiating circuit, we can clearly see that for higher values of frequencies, the value of the decibel gain is higher than compared to the lower values of frequency. From here, we can tell that differentiator circuit it acts as a high pass filter, as explained earlier. We can see that from the 2.7 kilo ohm resistor also. So it acts as a high pass filter. We'll see the difference between the board plots for the integrating circuit for 2.7 kilo ohm resistor and 1 kilo ohm resistor. Here for the 2.7 kilo ohm resistor, we can see that the value of the decibel gain is decreasing decreasing faster when compared to the 1 kilo ohm resistor. Like if we draw a tangent at any point in this graph, we can see that the slope of those tangents increases at a rate which is faster than the slope of the tangents in the 1 kilo ohm resistor case. So now we will see the difference between the results when we give a sine wave and a square wave to the differentiator circuit. So first I am going to explain, first I am going to tell the prediction of what is going to happen, then we'll show the results. So basically if we give a sine wave in a differentiator circuit, if we give sine wave as an input, then we will generally expect a cosine wave. And if we give a square wave, since it's differentiating, a square wave is going to have a rectangular pulse, continuous rectangular pulse. So at the edges of the square wave, the slope is infinite. So at that point, we should have a sudden peak in the values, and at the remaining places, the square wave is just a flat line. So at that point, the slope is 0. So when we give that to the differentiator circuit, at those points it will be 0. So basically, we should apply. So we should be able to see continuous peaks in the output when we give square wave.
This is the first sine wave for the question number 3. This is the first sine wave of amplitude 1 voltage peak to peak and the frequency 1 kilohertz, and the second channel is the same. The amplitude is 0.5 voltage peak to peak and frequency is 3 kilohertz. The output we get by the average of these two sine waves is over here, as you can see in the oscilloscope.
Here is the physical circuit for the question number 3, in which we have to take the average of two input sine waves, and from this, here is the circuit diagram for this question. We have taken the V1 and V2 as two inputs from the function generator which are in the same phase, and we connected it to the 1k ohm resistance, and we have connected it, jointed it and shorted with the non-inverting pin of the op amp number 1, and from here we took the feedback resistance of 1k resistance, and we have taken to the output from pin number 6 of the first op amp, and we connected the 2k resistance from then, and we connected this 2k ohm resistance to the non-inverting pin of the op amp number 2, and we took the same feedback resistance of a 1k ohm and we connected to the output, and we connected two non-inverting pins to the ground, and these two grounds are common grounded with the op amp ground, power supply ground. Thank you.